Welcome to this eLearn Security video lesson on Backdooring PE Files. In this video, part 1 of the series, we are going to cover the basics of smuggling a backdoor code inside a legitimate application without changing its behavior so that any user of this application will not be aware that the application he runs contains a hidden malicious code. We first need to find a suitable executable file that will serve our purposes. Currently, we are on Windows 7 32-bit, which fully supports ASLR. During the process of patching a binary, we will need to hardcode some addresses. Thus, the only target binary that will work for us has to be compiled without ASLR support. Unfortunately, most modern applications include support for ASLR. However, we should remember that there are still older versions of those applications, and as long as their user interface has not changed much, they can make a perfect target for backdooring and can be used in social engineering scenarios. We chose the 7-zip file manager. Although its latest version supports ASLR, the older one does not, and the graphics of the application interface doesn't change. The user running it will not be aware that the application version is not the latest one. The version can be seen in the file properties. We are using 7-zip from 2017. In order to download the software, we can use SourceForge. It contains archived versions in case you would like to experiment with other releases too. We will work on a copy of the original binary, which we will now copy to the desktop. Let's go ahead and run the application. The application is behaving as expected, and the user can go ahead and perform whatever function they would like to. Now, let's run the application within the debugger. We will use X32debug for that purpose. There are two breakpoints, as usual, when using X32debug. The first is upon attaching the debugger, and the second one is on the debuggy entry point. Let's take a look at the starting address while we are at the entry point. We'll need to remember it or note it down. So at this moment, if we know that no ASLR is in place, then we will examine a live example. Let's relaunch the application again. We can see that the entry point address is the same, which means that ASLR is not enabled for the application, and we can safely proceed. The first thing we need to consider when backdooring an application is where we should place our backdoor code. Unfortunately, the application does not seem to have any empty space, and if we try to overwrite some existing data, we might corrupt the application, rendering it unusable. If we go to the memory map in the main executable, there are sections which are standard parts of a PE executable file structure. Maybe we can add our own section and place our code there. Let's close the debugger. In order to tweak the sections, we need to use Lord PE and the eXDS hex editor. While you are likely to know the eXDS editor, Lord PE is a rather niche application, and at first sight it may look outdated. Although Lord PE was written a while ago, it still perfectly serves its purpose: editing PE executables. It can be downloaded from the following website. For this video, we have already downloaded it, and all of Lord PE's data is in a separate folder. We will now use Lord PE to add another section to the 7-zip executable so that we can later store the backdoor there. Upon launching Lord PE, let's go to the PE editor and browse for the 7-zip application. Here we see the executable's metadata being displayed. Let's click on the Sections button. We can see all the sections that were also visible in the debugger. Let's right-click on the last one and choose Add Section Header. Another section was created at the end. It currently has some default settings and is unusable, so we need to alter it a bit. Let's select the newly created section, right-click it, and then select Edit Section Header. We'll then change its name. For this example, let's rename it to XYZ, and we will also change the section's virtual size, which means declared, as well as the raw size, which means the actual size of the section. Next, we'll edit the flags by clicking the small button with the ellipsis at the end of the flags row. What is most important to ensure here is that our section should be writable, readable, and executable, as we would like to perform all of those operations in this piece of memory. Lord PE marks all of those flags by default for us. Let's press OK and then save so that the executable will be altered based on our changes. Upon reopening the executable, we can see that the changes we introduced were saved. The XYZ section now appears. But when we try to launch the application, it does not open. Instead, an error pops up. This is because the section was not defined. Rather, it is empty, so the operating system does not allow for the application to open since the metadata does not match the actual state. The simplest way to change it is by using a hex editor. Let's open the 7-zip application in eXDS and navigate to its end. First, we place the cursor at the end of the file. From the top navigation, choose Edit and Insert Bytes. In the byte count line, we'll update that to 1000, which is the exact size of the section. The fill pattern contains the exact bytes that will be populated in the section area. We are perfectly okay with just zeros. Afterward, we can save the file and then try to reopen the 7-zip application. the application now opens correctly. Let's open the application in X32 Debug and navigate to the entry point. In the memory map, we can see that our new section is there. Our next task will be hijacking the execution flow. We want the application to visit our section upon start and proceed with the execution only after it's done in our new area. In order to do that, we will need to alter the program entry point, but we need to be extremely careful so that we don't delete a single program instruction. We will need to change the first instruction. However, the push EBP instruction is only one opcode long. If we change it to something else, like a jump which requires a few more opcodes, the instructions next to push EBP will be corrupted. The number of bytes required for a jump instruction opcode is equal to the size of those 3 starting instructions. We will need to save the beginning of the file instructions and restore them after we add the code. Let's check it on a live example. We'll go to the memory map and copy the address of our newly created section. Now, let's highlight the first instruction. We will trigger the disassemble utility by pressing space while the instruction is highlighted. Then we'll change the assembly so that it jumps to the beginning of the section. We see that the first 3 instructions disappeared. We cannot save the program in this state since it will surely crash. Let's restart the debugger and now try to perform the same operation, saving those starting instructions for later use. Now let's mark and binary copy those 3 instructions. Later, we can simply copy and binary paste them from that form. Once again, we will copy the address of XYZ section. And now we can safely change the first instruction to jump to our controlled area. Now we can use step into to go through the newly created jump, and we land at the beginning of the XYZ section. As we made sure that our code hijacking works as expected, we can now patch the file and save it as another executable. Let's name it, and we'll add a number 2 to the end. Let's close the debugger and open the newly created executable that contains our changes. We will now work on that copy. As the debugger breaks at the entry point, we can see our jump being present in the entry point of the executable. Let's step into it. Before we do anything, we need to remember that apart from the requirement of restoring any deleted instructions, there is another important thing. The registers and flags contain the current state of the program. If they are somehow altered due to code added in the XYZ section, they will cause the application to crash further in its execution flow. For example, some variables saved on the stack will be moved or lost. Let's make a screenshot of what the registers pane looks like, as this is the real state of the program and we will reference it soon. The snipping tool may come in handy here. We will now save all of the registers and flags, as that is a requirement we should carry out before performing any operations. Since we would like to execute some code here, it will alter registers and the stack. We need to restore current registers and flag state once our code is done. The best way to achieve it will be to push all of them to the stack and then pop them again once our code is finished. Push AD and push FD are instructions that allow us to instantly push all registers and flags onto the stack. We'll first highlight the instruction and then press space to assemble. We can now introduce the push instructions. If we now step into those newly created instructions, we can see register values appearing on the stack. We can compare the previously taken screenshot with the current stack, and we can also see those values present there. Whatever happens in the XYZ section, as long as it's possible to return to the current state of the stack, will not have any negative impact on the application's legitimate functionalities. We can patch and save the application with the new push instructions before we continue to the next task. In naming and saving the new file, we will add the number 3 to its name. We can instantly open it with the debugger and head to the XYZ section. There is one more thing we need to do in order to successfully restore the execution flow in the future. As we restore the stack and registers to the original state before the jump to XYZ, we also need to return to the entry point. To do so, at the very end of our code, we will need to jump back to the first instruction that was not altered, which is the instruction next to our jump to XYZ section. Let's copy the address of that instruction, as we will need to use it later. After all of the instructions in XYZ are executed, we need to jump to the address next to the current entry instruction, so the application will behave in the original way. We know that these are opcodes for the first 3 instructions that got overwritten. After the state of the stack and registers are restored, we would like to jump back to the entry point, so let's save the address for later use. Now let's move on by using step into. We will try to imitate the shellcode using a short NOP sled. After the NOPs, let's place the register's recovering routine. Since push FD was the last instruction at the beginning, we will then start with pop FD, as the stack works in a first in, first out manner. In order to restore the execution flow completely, let's also paste the instructions that were overwritten at the beginning. We'll copy the raw bytes saved in the text file and binary paste them, ignoring the size, so that all the instructions get copied. There is one final thing that we need to add, which is the jump to the beginning of the program. The jump instruction can now be copied from the text file and pasted into the assembly window. Now let's step into all the newly created instructions to see how they work. We see that the registers were restored to their previous state. Finally, we land in the program's entry point like nothing happened. The program can now start its legitimate functionalities. As everything is working correctly, we can patch the executable. We can also see all of the modifications in the Patches pane. Let's go ahead and save it, naming it as our version 4. Now let's launch the application to see if it really works. We see that it starts as if nothing was modified inside. But when looking under the debugger, we see that our code gets executed. While the application behaves as usual at first sight, the debugger allows us to confirm that a custom code was executed. The next step will be to replace the harmful NOP sled with something more useful. Let's head over to the Kali Linux machine, where we will generate a MSF Venom payload. A quick check of our current IP address is required in order to generate the proper reverse shell payload. Using MSF Venom, the payload will be generated in hex format. It is important to choose a stageless payload as we want the whole reverse shell logic to reside on the victim machine. We also do not need to worry about any bad characters, since this is not an exploit buffer, but all those bytes will be manually saved into the target executable. Let's also prepare a reverse shell listener using netcat. Now we will launch the application and navigate to the XYZ section. If we paste the shellcode here, the highlighted instructions will disappear. Let's save their raw opcodes for later use before we implement the shellcode. Now let's copy the payload and paste it right after the register and save the instructions. We will use a binary paste with the ignore size feature. We can see that for some reason the address got corrupted. It is important to pay attention to such situations, as the application will not work properly now. Luckily, we have written down the proper return address, so let's fix the last instruction by highlighting it and pressing space so we can access the assembly pane. This is not the end of the changes in the Metasploit shellcode. A Metasploit reverse shell is a bit more complicated than a NOP sled. During its execution, there are stack changes, loops, and calls to Win API. While it's all okay as a raw shellcode, if we want to use it in a stealth backdoor, we need to alter some of its default utilities. There's already an article on the web that dissects Metasploit's underlying mechanics and gives a hint on how to fine-tune it. Metasploit, in order to constantly be active, utilizes the wait for single object function with the argument -1, which means that it should wait indefinitely. Since we want the shellcode to execute and allow the real application to jump in, we should disable the infinite waiting time, as in the article. First, let's navigate to the respective code in the disassembly dump. Then, let's change the des ESI to a NOP. If we take a look at this piece of code, we will notice that this is the function we are looking for. Let's eliminate the des ESI instruction by changing it to NOP. There is one last thing we need to fix. The Metasploit payload utilizes an exit logic, so upon finishing, it terminates itself. We don't want it here as it will kill our application, and we want the victim to freely use the software while our reverse shell is running in the background. So, in order to secure the application from such a scenario, we need to remove the last call EBP instruction. Let's change it to NOPS. Since it was occupying 2 bytes, it was converted to 2 NOPs. The first NOP is also a convenient place for a breakpoint. Let's place it by highlighting the location and pressing F2. Let's run the code. We see the execution is stopped at the breakpoint we just set. On our attacking machine, we also see that the reverse shell was spawned. Before restoring the registers, if we use step into, we can see that there are no registers saved on the stack. During the execution of the reverse shell, the stack was altered, and it is no longer pointing to the place where we saved the program state. Let's scroll down the stack to find them. If we look down in the stack, we see the saved registers and flags. We will need to alter the ESP so that it points back to the place where our saved values reside. Let's count the offset by subtracting the current ESP value from the desired stack value. You might want to use a Windows calculator in programmer mode. Remember to switch it to hex mode. Let's add the result value to ESP by assembling the instructions where the NOPs currently are. Unfortunately, its size is bigger than just 2 bytes, so our instructions at the end were corrupted again. Let's paste the instructions from a text file, and we also need to remember to alter the jump value so that it points to the proper address. As we are now ready to run the file, let's patch it and save it as number 5, and then close the debugger. We will now try to launch the last version of the 7-zip executable. Let's prepare the netcat listener and go back to the Windows machine. The 7-zip executable started normally. Please note that it is possible to use the software in a legitimate way. While on a Kali machine, there is a reverse shell running in the background. The potential victim can now use the application in a legitimate way, while access to their computer was gained. This is the most basic way to backdoor an executable file. However, you should be aware that since it is the most basic method, most AV products will be able to detect it. This is mostly due to a non-standard section with the RWX permissions that are being executed at the program entry point. Modern antivirus programs should have no trouble noticing that something suspicious happens within the application. Coming up next is the second part of the PE backdooring videos, where we will improve the backdooring techniques in order to radically drop the detection rate. And this concludes our video lesson on Backdooring PE Files Part 1. Thanks for watching.